Netflix accounts for roughly 15% of global internet traffic. Just sit with that for a second. Millions of users across continents, all requesting data at the same time. If every single request had to travel back to one origin server, latency would spike. Infrastructure costs would explode, and systems would fail under load. This is the problem CDNs solve, not just performance, but scalability, cost control, and resilience. At a high level, a CDN is a distributed caching layer. It sits between your users and your origin infrastructure. Your origin stays the source of truth, but instead of serving every request directly, it delegates delivery to a globally distributed network of edge nodes. Think of it like logistics. Your origin is a central warehouse. A CDN turns that into a network of regional distribution centers. Same product, shorter delivery path. Technically, each edge node acts as a reverse proxy, with caching, TLS termination, and request filtering built in. Requests are routed using DNS or Anycast. And here's a question worth sitting with. How does the CDN actually decide which edge node is closest to a user? Because it's not just geography. It's network topology, routing paths, and latency. From an engineering perspective, one metric matters more than anything else. Cache hit ratio. A cache hit. The CDN fully serves the request. A miss. Your origin gets involved. And that distinction directly impacts latency, cost, and back-end load. Here's something worth thinking about. If your hit ratio drops from 90% to 70%, what happens to your origin traffic? In most systems, it doesn't drop linearly, it explodes. Because suddenly, your back-end is handling far more requests than it was ever designed for. Now here's where things get subtle. What actually defines a cache hit? The cache key. This includes the URL, query parameters, headers, and sometimes cookies. And this is where many systems quietly fail. Two requests that look identical can be treated as completely different. A tracking parameter, a session header, a slight variation in request structure, and suddenly, your cache fragments. Here's a question that catches even experienced engineers. Why might two identical API calls never result in a cache hit? The answer is usually not in the API, it's in the cache key. Not all content should be cached. Static assets are straightforward. Images, JavaScript, CSS, video segments. They're versioned and safe to reuse. Dynamic content is different. User-specific data, authenticated requests, real-time responses. These introduce correctness constraints. So here's the real decision. Can multiple users safely receive the same response? If yes, cache it aggressively. If not, you either bypass cache or redesign your system. And this leads to a deeper question. Can you restructure your API responses to make parts of them cacheable? Because that's where real performance gains come from. Caching introduces a trade-off, freshness versus performance. TTL defines how long content stays in cache. Long TTL, better performance. Short TTL, better freshness. But what happens when your data changes? Before TTL expires, now you have stale data across your entire edge network. So you invalidate, or you version. But here's the question. How do you invalidate cache globally, across hundreds of nodes, without creating inconsistencies? At scale, this is not trivial, which is why systems use strategies like stale while revalidate, serve slightly stale content, while fetching fresh data in the background. Think about this. Would you rather serve slightly outdated data, or block users while waiting for fresh content? That trade-off shows up in real production systems. In real-world CDNs, caching is layered. Edge nodes serve users. Regional caches aggregate traffic. And an origin shield layer protects your backend, instead of thousands of edge nodes hammering your origin. Requests are consolidated. Here's a key question. If all your edge nodes miss at the same time, do they all hit your origin directly, or is there an intermediate layer that absorbs that load? This is where architecture decisions make a huge difference. CDNs typically use one of two models. Pull, demand-driven. Content is fetched when it's requested. Push, proactive. Content is uploaded in advance. Simple enough. But here's the real question. If your origin goes down, what happens to your CDN? In a pull model, availability depends on your origin. In a push model, you may still serve content from edge. That's a very different reliability profile. Modern CDNs are no longer just caching layers. They terminate TLS connections. They absorb DDoS attacks. They act as web application firewalls. And they run code at the edge, which means part of your application logic can now live inside the CDN itself. Think about this. If you can execute logic at the edge, what should still live in your backend? This is where system boundaries start shifting. Cloudflare, Akamai, AWS CloudFront, Fastly, all solving similar problems, but with very different trade-offs. Cloudflare, developer experience and edge compute. Akamai, scale and enterprise reliability. CloudFront, deep AWS integration. Fastly, performance and control. So here's the real question. Are you optimizing for ecosystem, latency, control, or cost? Because that's what actually drives the decision. Let's look at a failure scenario. Cache stampede. Content expires across multiple nodes at the same time. Every request goes back to the origin, and your backend gets flooded. Now think about this. If your CDN suddenly disappeared, could your backend survive the full traffic load? Because that's effectively what happens during a stampede. Good systems assume that scenario. At a high level, a CDN is not just a performance layer, it's a control layer. It shapes how traffic flows, how load is distributed, and how systems behave under stress. But its effectiveness depends entirely on configuration. Cache keys, TTL strategy, invalidation, observability, because a poorly configured CDN doesn't fail loudly, it fails silently, and that is far more dangerous. In the next episode, we go deeper into caching inside your application, because once you start thinking in layers of caching, you stop reacting to scale and start designing for it.